Okay, so for the last session of the day, we're going to cover a number of methodological issues in the way that we've been computing the summary exposure values. So just as a quick reminder, we have been calculating summary exposure values since GBD 2015. And the idea of this measure was to provide comparison in a single number in terms across a broad range of risk factors. And so the summary exposure value represents the risk, relative risk weighted prevalence of exposure, where 0 represents no excess risk for a population for that risk factor, and then a value 1 represents the entire population experiencing the maximum or highest level of risk. So we report SEVs on a scale from 0 to 100%. So a decline indicates reduced exposure, and an increase in the SEV indicates increased exposure. So to compute SEVs, we need two quantities. The first is the population attributable fraction. And then the second is the maximum relative risk. And I'll go into a bit of detail. Just
to note, this is a algebraic derivation, and it's not the actual definition. Sure. So I think it gets very confusing otherwise. Have you shown the definition?
I haven't shown the...
So the definition is prevalence times excess risk in the numerator divided by max excess risk. It just algebraically turns out to be convenient that this derivation is true. But otherwise, this is not an appealing conceptual.
Okay, so we compute this at the most detailed age, sex, location, year, and outcome. We also then generate an overall SEV for a risk factor across the outcomes, and I'll get into the details of how we currently do that. So it's important to remember also that for computing the SEVs, we use the mortality population attributable fraction, with the exception of those risk factors which only have a non-fatal effect, and there we use the non-fatal population attributable fraction. So that includes risks such as occupational noise, bullying, intimate partner violence, and occupational.
There is a component of mortality for intimate partner violence.
Not anymore.
Yes, there is.
Or could we drop HIV?
No, but there's femicide.
But, so that's true, but we don't have a corresponding population attributable fraction. Yeah. Okay, so how do we determine the maximum relative risk? So for categorical risks, it's pretty straightforward. It's, of course, just the relative risk at the highest category of exposure. So for suboptimal breastfeeding, that would be no breastfeeding. For water and sanitation, that would be the unimproved water source with no filtration or treatment. The question is on what we do for continuous risks, where those risk functions continue all the way out to out to infinity. And so for continuous risks, we estimate the maximum relative risk by taking the relative risk that corresponds to the 99th percentile of the global exposure distribution. And then for protective risks, of course, it's then the first percentile of the global exposure distribution. So here's a table of the 99th percentile of exposure at the global level across the categorical, across the continuous risk factors. I think the ones that make more sense to me are BMI of 36, blood pressure of about 170, LDL cholesterol of around 5 millimoles.
Now, I don't I think there's something not right with the low bone mineral density because high values are protected there. So
That,
I've inverted them.
okay. So we'll check that here.
it should just be shifted to the 1% column, I think.
Okay, now I do want to note that the 99th percentile of exposure is uniform it's the same across all ages, right? So that 170 of systolic blood pressure is the same, but the joint maximum relative risk currently varies by age because there's variation in the relative risk function by age. Now what that means is that the SEV can change age group to age group simply because the maximum relative risk is changing by age. So a couple of questions for discussion are, should we continue to determine the joint maximum relative risk based on the 99th percentile of the global exposure distribution? And then also, should we continue to allow these maximum relative risks to vary by age?
There's some alternative you're suggesting?
So for the relative risks by age, we could fix that by age at some.
Why would we do that? If we actually think the relative risks vary by age meaningfully, then the maximum XX risk is, just go back to the construct we're measuring, right? Current excess risk in a population compared to maximum. If the highest that you can have as a 20-year-old is much lower than the highest you can have as an 80-year-old, it's got nothing to do with the construct, right? You wouldn't want to fix them.
Yeah, and I think that's where bone mineral density is also a little different because we have a different comparator by age and sex. So it's relative, you know, so the TMREL is age sex dependent.
TMREL is age sex dependent for bone mineral density. Why?
In a long discussion, we decided that we would do it based on the 99th percentile of what we see in Haynes, and arguing that there is an inevitable sort of loss of bone mineral density with age.
How long have you been doing that?
Oh, it's quite a few rounds.
Okay, so that also means the max relative risk also varies by age.
Can I ask about the 99th percentile of the exposure distribution? So that, to come back to some of the discussions today, presumes a monotonic risk function, right? Really, what you mean is the 99th percentile of the global risk distribution.
Yes, we don't mean the 99th percentile of exposure.
Okay.
We mean the 99th percentile of the global risk distribution.
Then that makes sense.
And that's exactly what we're trying to approximate when we get to the joint risk distribution. That's that's what we mean by that.
And how sensitive is it to this 99th percentile? What if you do 98th or 95th? Then have you looked at that?
Well, if you look at those numbers, you go to the table that Steve has, you don't want to lower blood pressure below about 165, as the max. I mean, these numbers, we thought about lowering them, but that would be.
And 36 BMI.
No, these are sort of reasonable numbers, right? You wouldn't want to go lower than that.
1.48 bone mineral density. That is pretty strong bones.
Is it?
Oh yeah.
But it's the.
But I think it's because it has an age gradient. You're not taking that into account.
I mean, that's actually one where, Okay, so let me move on to how we determine the SEVs for all outcomes for a given risk. So in other words, the overall risk SEV. So the risk outcome specific SEVs at the most detailed risk cause, age, sex, and location level. Then to get the SEV across the outcomes, we do a simple average of those SEVs to produce the final risk all outcome SEV. Now, for most risk factors, this doesn't make a whole lot of difference, right? Because there's often just a handful of outcomes associated with a given risk. It does have quite an effect for the risks where we have lots of outcomes associated. So this shows the distribution of SEVs at the global level. So this is all age, both sexes, across.
What are the units on what? On X?
This is just the frequency, a histogram.
On X?
That is 0 to 100.
0 to 100.
So you can see that for smoking, we have SEVs for some outcomes at almost 20, and then some very close to 0.
An SEV close to 0 on smoking.
It'd be one with probably an extremely high relative risk. So it's probably lung cancer.
But on lung cancer, they're using, that just seems suspicious to me, right?
The one at 0 is smoking Parkinson's. So because that is a protective effect, we cap that at 0.
Oh, I mean, we should just be excluding it from the SEV calculation.
Okay.
So same with alcohol, that's the protective effect.
Yeah,
That'll be, is that diabetes?
I don't remember the
IHD?
cause off the
Yeah,
top.
those would be the
But
ones.
it would be the same protective.
Okay. So I think the potential alternative approach is to weight these according to the cause fraction. Right? And we could do that, say, at the global level. Again, it's only going to
The
have
cause fraction as of the total attributed to.
again, it's only going to have an effect with these particular risks and lots of different outcomes.
So wait a second, what would you weight by? No, it wouldn't be the cause fraction, right? Let's say, smoking has a minimal effect on an outcome that's really large. We're not going to weight that SEV. I mean, what would be the logic of weighting that SEV heavily? It's not.
I guess that would be the attributable.
Trivial burden. I mean, problem with that, we should see what it looks like. I mean, the advantage of averaging is it's a little bit more robust to various measurement type errors.
The meaning
But
of the average,
the only measurement error here is really, so the only difference across
Measurement error is riddled across the GBD, my friend. So,
right, no, but in terms of across the different risk outcomes, the only difference is really the maximum relative risk.
Just measure with enormous error. Right. That's the whole point. I think, if we want to do some sort of item reduction here, I don't think weighting by the cause fraction makes a lot of sense. You think of each of these is meant to be an imperfect measure of risk-weighted exposure. So, and we absolutely know that max relative risk, think of how sensitive it is to monotonicity versus not, the max relative risk versus the log linear. These are exquisitely sensitive because you're going out on the tail of the distribution. So these are all measured with horrible error. I think we might want to try something like, factor analysis or some dimensionality reduction method that's looking for the common thing here. I just feel like we should be careful because we may weight the one thing that has a log linear hugely, and the next year we go and put a non-log linear, and suddenly these numbers change dramatically.
What we're trying to do here?
We're trying to get a single robust measure of exposure that's in the space that we care about. And since we have dichotomous, polytomous, and continuous risks, we need to convert all those into some common 0-1 scale. And it turns out this is the optimal measure because of its algebraic relationship to the path for forecasting. So it turns out forecasting SEV is like how the whole system works for forecasting. Because we can reduce all this complex information into one number, forecast that one number, and then the algebra just falls out beautifully to give us the population level, scalar that we want.
And you wanted to compare across risk factors. That's what you.
The biggest use for us in terms of the description of the GBD is a forecasting use, but the biggest use is to get trend in the SEV, and it turns out that the RR max just falls out of that. So when you compute rate of change in the SEV, the RR max disappears. So the one that, for example, in the risk factor paper that we use a lot is the rate of change in SEV. And that's great because we don't actually care about this error in the RR max. But some people want to look at maps and look across risks. It's not so meaningful across risks, right?
No, it seems impossible to make it really comparable across different types of
Across risks.
So within a risk, so it changes from 0.2 to 0.4, and what does that signify? That's.
Well, if you calculate the annual rate of change,
Yeah.
you get the rate of change in exposure. And what happens is once we can combine them, which we've tried to do now, into all metabolic risks together, all environmental risks, then you can get the big picture trends in risk exposure.
So primarily, it collapses the information in the exposure distribution into one number.
Yeah.
Right.
But for the actual application, actually very difficult using the SGB because we want to know exact the exposure level in future.
Yeah,
So
we
for the
need to be
SGB,
able to
very
back
difficult
out the distribution.
Yeah, it can't.
Important.
It
It's
can't.
high on our list, yeah.
We have problem.
Not work that out yet.
You just have to make some assumptions, right? It's not.
Okay.
But how surprised are you that those values by outcome vary so much?
So values by outcome vary so much.
In the bar chart.
It's not surprising, right? Because the risk functions vary quite a lot across the outcomes. So let's take lung cancer versus cardiovascular disease.
Well, it's not that the risk function varies, it's that the shape of the risk function varies. Right? It doesn't matter because if you multiply the risk function by a scalar, it doesn't do anything. But it changes the units, right? So if we take RR max and multiply by some arbitrary number, you'll move these units around, right? What I would be much more concerned is if the rate of change across these was different. And that would be pretty interesting to look at. But otherwise, the units are sort of arbitrary, right?
So even for the same exposure, you're not inclined to compare these.
Oh, we average these. So we never. I think this is the first time we've looked at them at the risk outcome level.
You're not inclined to compare the values for
No,
different
because
outcomes.
it's a shape of that function, and what do we say the max risk was? And if we just went up here, suddenly the SEV will be depressed down to a smaller number. So, I think unless there's some way for us to rationalize the computation of the RR max or stabilize it in some way.
But it would be very interesting to see where are the different causes in these plots.
Yeah, which causes are where.
Yeah.
But it is strictly a function of the shape of the risk function, right?
But still, I'd like to see.
Yeah,
where.
no, absolutely.
We can give that to you. Sven.
Yeah, I can.
We can make it. Okay, so let's move on to joint risk, which Chris mentioned earlier. So in GBD 2019, we've moved to also computing the joint SEV. So the SEV for groups of risk factors. So in previous cycles, we've only done these for individual risks. So to go back to the earlier formula, what we then require is the joint population attributable fraction and then the joint maximum relative risk. So for the joint population attributable fraction, the key issue here is to determine the extent to which a risk's effect is either partly or wholly mediated through another risk in that group. And to determine that, we use the available cohort data
Sorry,
publications.
Steve, just go back a sec.
Sure. What do you want to go back to?
The graph for smoking. I guess the right way, given that for the 2 pagers and the risks this cycle, we've sort of done the right thing, which is we have generated the all-cause risk function for a true global cohort. So rather than weighting the SEVs, which gets muddied up with this R max, first we combine them into the all-cause risk function, and then we just do one SEV off that. That actually will be stable and will be meaningful. Right?
So,
Doesn't solve his problem, though. He has to.
but I guess I'm not quite getting what you're suggesting.
So we have a bunch of risk functions.
Right.
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 And for each cause. And for the 2 pagers, we combine them into an all-cause mortality relative risk function. Well, we could compute the smoking SEV just from that. Then we just get one number. And that one number is actually comparing smoking in totality to a population at maximum risk. It's your idea, but just doing the weighting before we compute the SEV.
And so we use the all-cause path.
Oh, you mean back to your algebra thing? We'd have to just check the algebra. I think so.
Would all cause there represent only the valid outcomes or all possible causes, like different amounts of risk?
Should make no difference, I think.
Wouldn't it be smaller if you accounted for all possible?
Gets scaled by the max.
Yeah,
So
the,
that
the
it falls
path is
out.
small, the path would also be smaller, right? So this is, anyway, I think we have to work through the details of that.
I think it gets scaled by you have a fraction of all the causes that are in the computation, but then that falls out of the max too, right?
Well, you just have to make sure that if everybody's at maximum exposure, the value is 1. Right. So probably has to, just have to see what that. It shouldn't matter, right?
Okay, so to determine the mediation factor, we look through cohort studies, publications, to determine the fraction, the excess risk that is mediated by other risks. So a typical way to do this is to estimate the relative risk, not controlling for the risk for which it's mediated through. So if we're looking at BMI, we would determine the relative risk of BMI not controlling for FPG. So that would be the relative risk total here. We could then repeat the analysis controlling for FPG. That would be the relative risk non-mediated part. And then the equation here defines the mediation factor. Once we have the mediation factors, we can then adjust the relative risk. But what I want to do is, so the mediation factors in the GBD is an area that we have perhaps not spent very much time looking at carefully over the cycles. And so it's actually useful to see where we're taking into account mediation currently. So let me just show you the current matrix of this, because I think it highlights a number of holes in our mediation matrix. So let me just highlight what this table is showing. So first column is the risk. The second is the risk that it is being mediated through. We have the corresponding cause and then the mediation factor. So here, this tells us that 5% of the excess risk diets low in fruits on ischemic stroke is through high fasting blood. And then the second row down says 6% of the excess risk of diets low in fruits are mediated through LDL cholesterol for ischemic heart disease. Now, in looking through this, we have a pretty comprehensive mediation matrix for most of the dietary factors. That becomes more sparse as we go down the list.
Sorry, Steve, are those additives? So you want to get the non-mediated, you just subtract all of those or no?
If you want to get the non-mediated, you need to subtract all of them.
They're additive, yeah, I believe.
But there's certainly some holes.
You're not sure they
I don't
can
know.
be.
All right, would they be additive?
Seems odd that they would be additive.
Yeah.
We don't treat them as additive. We do 1 minus the cross product of 1 minus mediation factors. So we're treating these not as additive.
Okay.
Multiplicative.
Yeah.
Okay, but for example, low physical activity, the only mediation here is on fasting plasma glucose,
Not blood pressure?
blood pressure, not on BMI.
BMI tricky, right? Because you can eat your way through whatever physical activity you have.
But you would expect a blood pressure effect here, for example.
Certainly would.
But I think what this highlights is that the mediation matrix, I think, is an area of work for us. And I think the question is how we organize that, because it involves a number of these kind of pooled cohort analyses. And it's probably more efficient if we're looking at them in an integrated way rather than, for example, team by team. And I think that's why it's generally dropped off the list for us, cycle to cycle.
Where do they come from? Those
Literature review.
numbers?
Literature reviews,
Reanalysis.
of cohorts, etc.
It can certainly do with an update. Question, who does it? Who does it?
Yeah, but we really only have mediation for BMI, cholesterol, FPG, physical activity, and then the
We're missing some here, like fruit, fiber, right? I thought we had 100% mediation for.
No, it wouldn't be. Why would it be 100%?
Depends on
Fiber, whole grain.
like all of fiber is accounted for by diet. So in aggregate, fiber drops out entirely.
I've just filtered these.
There's no non-diet fiber, which sort of makes sense, right?
Well, we have a number of these. I just filtered off the
Ones.
ones.
The lead is through blood pressure.
Right.
Okay, and I think with this new analysis for chronic kidney disease, we ran the analysis with and without controlling for blood pressure. But there it's a more tricky thing because it's both the pathway from chronic kidney disease to cardiovascular outcomes through blood pressure, as well as probably a component that it is mediation. So we decided then that we would err on the side of saying, well, let's control for it.
I mean, the only way to untangle that is if you have repeat measurements, right? Or even then, I guess it's true.
Yeah.
Okay.
What are you planning to do with temperature and mediation?
Haha.
Or
Like
in
a thorny set of-
education and mediation.
It's been a thorny. We currently, I think Mike's strategy is to say that he thinks the evidence is unconvincing about that it goes through any particular pathway.
Temperature?
So right now, there's no mediation. We had lots of debates about this. Seems unlikely that some of it's not through blood pressure.
And the problem is because of the
Temporary.
source of the relative risks, we can't, there's no risk factor information, right? And the factor registration system data that we're using. So can't look at that mediation analysis within the same data set for which we're deriving the outcome. Okay, so just very quickly, what we do is use those mediation factors, subtract off the excess risk, whether that's through mediation, we get an adjusted relative risk, recompute the path, and then we can use the standard joint path formula, which is 1 minus the product of 1 minus the individual paths. That gets us the joint path. I think we have a general question around how we more comprehensively determine mediation factors in GBD. But to move on, so we covered this in the Scientific Council this morning, but let me just reiterate it. So,
just 1 sec, we're not seeing those slides. Can you share?
I have a problem in the mediation matrix while Steve's doing that, which is we only know one direction of that matrix.
have you seen that?
So we know lead is 100% through blood pressure, but what we actually need to know to solve for forecasting is how much of blood pressure is from lead in different settings. Because what you'd like to do is you'd like to have a lead deleted systolic blood pressure, forecast that, and then add back on lead. So anything that's upstream you'd want to delete, but that requires information that we don't currently have. I had not thought about correctly.
But if it's 100% through blood pressure, can't you back calculate then?
How would we?
Well, all of,
We know the effect size.
Oh, because we have a relative risk. Oh, I guess we can back it out. Yeah. Just need to play with the algebra. That's right. No, you're right. We have to have both. You need to know the mediation and the relative risk.
Yeah, we've just never done the computation.
Yeah, no. All right, so that's okay.
so Steve, are there any of these examples where you have both continuous and categorical risks?
Mm-hmm.
Because that would be the problem that I was talking about today, right? Which is that you're taking an average, but for the continuous ones, it's the average of the first percentile highest, first highest. The continuous, it's whatever percent of the population that highest category comprises, right? And then you need to reweight them somehow.
Yeah, there's a small number of cases where we have continuous and categorical. They're somewhat holdovers from previous cycles. So I think Mike illustrated one earlier today was air pollution, where we have a dichotomous effect of household air pollution on cataracts, and then the remainder.
But we can. It's somewhat, it just simplifies the problem, but we can start with the observation that the dichotomous is still, the exposure is continuous. It's just a step function for the relative risk. And so then we don't have to, right now, we run them completely separately. And it creates huge problems for forecasting because we forecast them completely separately. So there's no need, right? You just say it's a step function of the risk. So that's one step in the right direction. And then in terms of your point, M's been arguing, well, we know the shape for all the other outcomes. So where we have just the dichotomous, should we try to fit a spline that goes through the midpoints of the exposure?
We don't have any risks that we think are step functions. So a step function just means that we've estimated the continuous risk function poorly.
Yeah, which is why I like the pushing it into that framework, because then it makes it very obvious that that's just not a credible risk function.
Okay, now to get the joint maximum relative risk, we can't simply take the product of the individual maximum relative risks, because that is going to represent a point on the joint risk distribution that is above the 99th percentile.
Represent a very small number if you have 10 risks.
So to approximate what the 99th percentile of the joint risk distribution is, we go through the following steps. So first, for each individual risk, we look at the distance between the 99th percentile, so the maximum relative risk, and then the relative risk at the global mean. We compute the ratio of those two quantities. We then compute the geometric mean across those ratios. Separately, we compute the product of the individual relative risks at the global mean exposure level, and then we just multiply the two together to approximate the joint maximum.
Now, Pong, who's not here, did some simulation. The right way to do this, which is trying to write the code, is just to actually simulate the whole joint distribution, line people up by risk, not exposure, and get the 99th percentile.
That's actually what we discussed on the council.
So Pong's tried that, right? And that's the simulation he did to say that this was an okay approximation, but that's the right way to do it.
But I just have some visuals showing the distribution of those ratios. And this is for ischemic heart disease across all risks, age, and sex. Now, to note, part of the distribution also comes from the fact we have age-specific maximum relative risks as well. And that includes, some of the older age relative risks for IHD are close to 1.
So you would only want to look at this
by age.
Are you taking the geometric mean by age?
Yeah, I just put them all into this plot, but it would be by age.
Okay, so my last question for discussion was alternative approaches for estimating the joint relative risk, but we've already discussed that as using simulation as an alternative.
Who's going to write that?
The simulation? I thought Pong was doing it.
No. Because you need to do this every year, right? So it has to be in the main central comp side.
It's very similar. It's very similar to Como.
It's easier.
What's that?
We're getting rid of Como.
It's Como's new purpose. Como.
AB likes to do simulations.
Okay, well, I'm not sure if there are other things that you want to cover on SEVs or Emil as it relates to forecasting.
Well, if we go to the single rolled up risk SEV, it has a certain appeal to it. I think then we still have, on the FHS side, still have to figure out a model that predicts from the overall SEV to the outcome specific SEV. You have a model to do that, right? Now. You just have to think about, is there a better model?
What's the model currently?
What is it? It's the logit difference in the overall compared to the risk outcome. Something.
And that works?
Sort of.
One individual risks, not too bad.
Not too bad.
But
I guess the question is, do you need a model if it's really just mostly driven by the value of the RR max? Or put it another way, I suspect if you're trying to go from the overall smoking SEV to each of the outcome SEVs, if you stick on the right-hand side, the RR max of that outcome compared to the average RR max, it's going to be a very predictive model. And I don't think that's what we're doing. But that should work really well. Right? 'Cause that's essentially, it's the difference between the two that's scaling the different outcome. Or, there's a little bit of the shape of the function as well. That'll be second order compared to the scalar effect.
And then I think the last challenge is to address what Stefan was talking about, which is going from SEVs back to the distribution of exposure.
Yeah. That, I think, I've played around with that and just writing that down. Obviously you're losing information, right? So the SEV is some function of mean, measure of dispersion, and shape of the distribution. So you got three things that get reduced to one thing, and so we have to make some assumptions about the missing, so how to go back from the one to the three. We know the shape of the distribution, right? Because we model it in the first place.
Isn't that what Nick was saying, that he shifts the mean and then applies the same functional shape from the ensemble?
Well, we have whoever's modeling the risk has a parametric or quasi-parametric, ensemble or whatever it is. So we can just take that distribution. So all that we actually need to do to go from one number to two numbers, which is the mean and some measure of dispersion.
I mean, or you could, instead of projecting the one number, project your two numbers.
Gets you really lots of ugliness.
Why?
Because you get differential trains, and then in 80 years from now, you get completely impossible distribute. We tried that like 2-3 years ago. We got really horrible stuff. And then then you have to build in like all sorts of protection in your modeling framework to stop that happening, when this is just a much more straightforward way to do it.
Right, but fundamentally, it's this. You're trying to do the same thing because you're projecting forward the one and saying what's happening to the other one. So instead of actually projecting it explicitly, you're going to project one and then wave your hands about what's happening to the other one in relation to it. So that's not preferable.
It is, because the SEV has this very simple relationship to the path. So when we project the SEV, the path falls out in sort of like that. And whereas what you're describing, we have to go through the whole path calculation. It would just be computationally basically impossible, because already it is super complicated.
But because the SEV is not a sufficient statistic for the whole distribution, it seems like instead of trying to reverse engineer that once you have a projected SEV, you should find something else to project.
Well, you could model mean and standard deviation conditional on SEV. And then if it's a conditional quantity, you would still take your SEV forecast, and then you could model those two quantities.
Yeah. Or just one of those conditional on SEV. So the standard deviation could be
Because the other one is identified.
Oh, yeah, the other one. Right. So that would be reasonable. Do it conditional on the SEV, because then we don't have to change the machinery. You don't have the computational load. That sounds like a reasonable idea. So you could do SD conditional on SEV and model that.
And also, we forecast, I think, logits-based age standardized SEV.
I mean, it still doesn't get you out of the problem.
No. That sort of complicates it.
Not really. No. We want to, all that's doing is building a strong relationship between risk exposure over ages. How do you go from the age standardized to age specific?
We found it out again. Just reverse.
Reverse engineer?
Yeah.
Same weights.
I think we used the same distribution, just what you started with.
Worth a deeper dive.
Okay. All right. So I think we're done for the day.
Thanks, Dave. Anybody remind us about dinner? Oh, goodness.
6:30.
Thank you, Joshua.
You need the one from IHA.
And it's printed on such lovely hard paper.